Okay, let's begin. So, nothing really new to cover with curve sketching. Actually, going through the remaining examples would be pretty much more of the same. So, we're just going to move on to the next topic, optimization. Optimization problems, whenever they show up, they will also show up as word problems on your tests and exams, your exams and quizzes. So I summarized the steps for you in a handout, which it's online if you, so you should have printed that out. Optimization. So we're going to talk about what this is and then go through a few examples. Just like related rates, it's pretty much always the same strategy. So in the box here we have the 6 steps that we want to go through to actually solve an optimization problem. And you might wonder, what is optimization? So this is, there are non-calculus ways to talk about optimization, but of course for us we care about the calculus methods. So here we're going to use calculus to design the best possible scenario given some, well, I'll tend to call it constraints, but it's basically restrictions that you might have. And that's optimization. Besides linear approximation, this is one of the most pervasive uses of a derivative. As like I said, there are cases where the derivative or calculus isn't the way that you would kind of do problems like these. You know, the world can be more complicated than calculus can handle, but a lot of times we can use calculus to be able to do this. So basically what we want to do is make something as good as possible within certain constraints. And in real life, there are always constraints. You always have limited resources, limited time, limited something. You can't just do whatever you want without restriction. You will always have restrictions. So once you want to make something as good as it can possibly be without restriction, one possibility is for you to be able to figure out what would give you the best outcome is to use calculus, and that is because since best can often be interpreted in terms of, turns out, maximums and minimums. So depending on the context, there are times when finding the largest possible value of something or the smallest possible value of something is going to give us the best solution. So when it comes to, for example, profit, we tend to want to maximize profit. So if someone is talking about profit, the best possible scenario is what do we have to do to make the most money possible? And that's a maximization problem. Oftentimes you want to minimize something like cost. Okay, so what is the best possible scenario to have our costs as low as they can possibly be? But again, you can't just make an infinite amount of profit, you will have restrictions. So within the context of these restrictions, you want to really push the envelope and really get as large or as small as possible given the restrictions that you have. And when you solve such a problem, when someone tries to solve a problem, we say you're optimizing the situation, that is called optimization. And for us, there will be 6 steps that we need to go through to get this process completed. And I actually like going through the first example while I illustrate the steps. And so the first example tends to be a very easy example. It's probably not something I'd put on a quiz or a test, but it's a nice problem to actually illustrate what we're going to be talking about. So how do you go about optimizing something? What does it mean to actually optimize? Well, it depends on the context. So let's actually work through and illustrate the steps using example 1 in the handout. And so 1. A farmer has 100 feet of fencing, and he wishes to make a rectangular enclosure. Okay, so that's the scenario. We have a guy that has fencing, wanting to enclose a rectangle. If he wants the enclosure to encompass the maximum possible area so that he can plant the maximum number of crops, what should the dimensions be? Okay, so that's your situation. Okay. So here he wants to make something as large as possible. He wants to cover the maximum possible area. He wants to cover the maximum possible area, but he doesn't have an infinite amount of fencing to do this. He only has 100 feet of fencing. So that's the restriction. He wants to make the area as large as possible, but the restriction is the amount of fencing that he has. So step one, you are to read and really understand the problem, which we just did. Step two, also similar to related rates, you want to draw a diagram if possible. Necessary. And of course you're going to label intelligently. Right, so anything that you don't know, you're going to label with a variable because that can possibly change. So in this scenario, we have a farmer wanting to build a rectangular enclosure. A rectangle is obviously going to be the diagram that we want here. Now, of course, what makes this problem a problem is that there are many possible rectangles that he could build, right? Where the length of the fencing is going to add up to 100, right? You could have 10, 10, 40, and 40. You can have 20 and 20, 30 and 30. 25, 25, 25, 25. There's a lot of different possibilities here. He wants to find the best one. The one, and best, according to him, is the one that gives you the maximum area. So because I don't know the length and the width, I'd probably start out by just labeling them. I don't know what the length is going to be. I don't know what the width is going to be. So that's my diagram. Now in the third step, we are going to set up some equations now to actually start on getting a handle on the situation. The difference between, one major difference between this and related rates is that we now need two equations to describe the situation, not just one. Because you see, there are two things going on. There is the thing that we want to make as best as it can possibly be, but then there's also the constraints. And it turns out we'll have an equation that describes each of them. So in step 3, we're going to describe what's called the constraint equation. And we're going to also describe another equation called the objective equation. Now, the constraint equation, that's the equation that's going to describe the restriction that you have. Right? So this guy should be an equation that describes your restriction. Or your constraints, right? This guy is going to describe what you want to actually optimize, or what you want to maximize or minimize. And in this scenario, we actually want to minimize something, maximize something. We want to maximize the area. Now the thing with the constraint, once you read the problem, step 1, you would recognize which equation should go with which, because the restriction is always going to be the something that's given to you. You're not going to have a choice of what it should be. It's going to be, that's the reality. This is what we have. So usually it's going to be the guy that you're given some value for, and that has to be the value. So what is the constraint in this situation? Yeah.
The perimeter has to be 100 feet.
The perimeter of this rectangular enclosure needs to be 100 feet. He has 100 feet of fencing. Doesn't have all the fencing he wants. That's his restriction. So the perimeter in this case is your restriction. So here, that is perimeter. Now what's the perimeter of this rectangle?
2y plus 2x equals 100.
2x plus 2y equals 100, or I can say x plus y equals 50. Right? That equation describes the restriction that I have on my variables that I came up with in step 2, and they tell you what it has to be. You have no choice. That is your restriction. That is how many resources you have. Now, what do we want to maximize? Area. So here we want to maximize the area. So what would you say is an area equation? Yeah, length times width. So A equals X times Y. Okay. And that is called your objective equation. So you have two equations. One describes your restriction. That's going to be the thing where they tell you the value. This is the value. This is how much fencing we have. That's it. You have no choice. That's your constraint. Then you're going to have the thing that you want to optimize in that under these constraints. In this case, it's area. So what we really care about is this function over here. Now, the issue with us is we are in Calc 1, not multivariable calculus, so dealing with a function with two variables is difficult. And so what we want to do for the next step is to eliminate one of the variables in the function that we care about. That brings us to step 4. We will always solve for one variable in the constraint equation. And plug its expression into the objective equation. In the constraint. Okay. So I care about the objective. There are too many variables though. I'm only a lowly Calc 1 student, so I need to get that guy in one variable. So what I'm going to do is, starting with x plus y equals 50, I can actually solve for one of these guys. In general, it doesn't really matter. There are cases where it might be easier to solve for one than the other, but in general, it doesn't really matter who you solve for. Pick a guy, solve for that guy, and then replace that guy in the objective. So this means your A is going to be 50 minus y times y, or it's going to be 50y minus y squared. So now you have the objective in a single variable, right? And that's the point of step 4. We want to be able to describe this thing that we want to maximize or minimize in terms of a function of a single variable. This brings us to step 5. Now we're going to do the work that we want to do. We want to maximize the area. Now, technically speaking, what this means is that we want to find the absolute maximum or minimum of the quantity in question. Now, it's worth mentioning that typically the endpoints will not give you the solution. If you think about the maximum possible value of one of the lengths of this fence, that would be 100. The minimum possible value would be 0. But of course, in either of these cases, you would not obtain a rectangle. So those would be the extreme values, the endpoints, right? But usually that's not going to be the case. So here what we're looking for is the local maximums and minimums. But in general, you should be looking for the absolutes. In Calc 1, those are relative solutions, but I've seen situations where those are the solutions. So knowing that we need to find the maximums and minimums, what do we need to compute at this point? Yeah, the derivative. So we know that if we find the derivative, we have a requirement on that guy that will tell me when a max or a min will occur. So according to us, maxes or mins, if they happen in the interior, they will happen at critical points. This is where the derivative is 0 or undefined. Now, the derivative here is a polynomial. It's never undefined, so I'm simply going to solve for when this is actually 0, and this gives me y equals 25. Now what we can do is we can make sure to check that this actually gives us what we want. Minimum possible value for y is 0, maximum possible value for y is 100, so now we want to test 25. I'm going to pick a random number over here, say 1, pick a random number over there, say 26, and I'm going to plug it into the derivative. If I take 1, plug it into here, I would get 50 minus 2, that is clearly a positive number. If I take 26, plug into here, that'll give me 50 minus 52, and that is clearly a negative number. So the function is increasing here and it's decreasing there, so that means this is a maximum, and that's exactly what I want. Now, again, another general statement here. In general, if you have only one answer, that's going to be the answer. But really, you should test it if you have several answers. Sometimes there will be several possibilities, and it's not really obvious which one you would pick. Obviously, here we're talking about the length of a fence. So even if we got a situation where we got a 25 and maybe a negative number, you can ignore the negative because it's never going to be the answer of the negative. It doesn't make sense for negative length. But if you have several positive answers, you want to test them to see who's actually giving you the most or the least. But we're not done. This leads us to the final step. And similar to the final step of the related rates problem is answer the question. Okay. So the question is going to ask you for something very specific. And in this case, it asks us for the dimensions. So knowing one side length is not enough, I need to find the other one. So the thing is, if y is 25, I know that my x will be 50 minus y. So my x is also 25. And so I can say the dimensions here is a 25 by 25 foot enclosure. Or you can write out length equals 25 and width equals 25. Either way. Now the question could have asked for something else. The question could have asked for what is the maximum error, for example. And if that were the case, I would simply take this y equals 25. I would plug it in here, and I would give them that answer. So it's very important that you read what you're being asked for, make sure you know what they're asking for. And that's pretty much it. That's optimization in a nutshell. Right? A situation is going to be described to you. You have to understand the situation, draw a picture to fully understand the situation, and you need to come up with two equations. One is going to describe your restriction, the other will describe the thing you want to maximize or minimize. This will, of course, be the guy you care about, so what you're going to do is solve for one variable over here, plug it into there, because we don't know multivariable calculus. So once you do that, you'll be able to get the function that you care about in terms of one variable, and at this point you'll know how to find maximums and minimums of that, because we know they'll either occur at the endpoints or the locals will occur when the derivative is 0 or undefined. Once we find these points, and of course we test them, we can then answer the question. And yeah, that's it. For this particular problem, there was a non-calculus way to do it. Do you see what the non-calculus way to would be? If you didn't. Let's say you didn't know about step 5. You didn't do step 5. Could you have answered the problem? I mean, these would be the same so far. So let's say you knew everything up to step 5. How would you figure out the maximum of this function? Yes. Well, what kind of function is it? Your objective, what kind of function is it? Huh? a very specific kind of polynomial. How do you describe it? A equals 50y minus y squared. What kind of polynomial is that? Yeah,
Is it a problem?
it is a problem. What would be, how would it look, this problem? If you were to sketch that function, sketch a versus y, what would it look like? What is a problem? What would it look like? Yeah?
You know, upside down.
An upside down problem. So if you were to sketch this guy, like that. Right? If you have like the vertical and horizontal axis being a and y. So if you know that's your function, how would you find the maximum of such a function? Yeah? Minus b over 2a. What does that give you? That would give you what we call the vertex. And here your b is 50, your a is minus 1. So you can find the y value for that by minus b over 2a. That will be minus 50 over 2 times minus 1. And that will mean that your y needs to be 25, which is exactly what we found here. Now, of course, why would we need calculus? Well, for the cases when we don't have a problem, is when we need calculus, right? Because there's no general, remember we've discussed this before, there's no general vertex formula for any random polynomial that I give you. In general, finding the maximums and minimums are kind of really hard. So, this case, we had a parabola. This was a quadratic polynomial, and so we can find the max or min by the vertex. But life will not always be that easy. And let's actually do another example to see that. Again, this one's not going to be terribly difficult either, but if memory serves, it's not going to give us a polynomial, a quadratic. Okay, let's do example 2. Design an open rectangular box with square ends on the left and right side, having a volume of 36 cubic inches that minimizes the amount of materials required for construction. So that is the new problem. We need to design a box. It will be open. 1. Great. Okay, so now we know the goal, we know what's required. 2, let's draw a diagram of what's required. This is going to be a box. It's going to be open, so there's no top. And now I'm going to label it. I'm told that the left and right side were squares. So let's just imagine that here there's the front, that'll be the back, this is going to be the right, and over here is going to be the left. Okay. Let's start labeling this. What do you want to label it? How do you want to label it? Yeah.
You label the height and width both x since it's a square, and the depth y.
So we label very carefully here. We don't want too many variables because again, we don't know multivariable calc yet. So the minimum amount of variables, the most amount of variables we want here are 2 of them. And so because I know the left and right side are squares, I use the same variables to represent the length here, and then some other variables to represent the other dimension. Okay. 3. What is the constraint and objective here? What's the constraint? Yeah.
Surface area, maybe?
is it?
Look, you can either have the whole surface area, or you could have the volume as
Well, it's not either. There's definitely one of
I'm
those.
just a-
That's right. So the problem says design an open rectangular box with square ends on left and right, having a volume of 36 cubic inches that minimizes the amount of material used. So if that's the question, what would you say is the constraint? Yeah? Volume is the constraint. Constraint is always going to be the guy where they give you the value, right? You don't have a choice. That's your restriction. Constraint here is volume. Constraint is the volume must be 36. And again, I know that's volume. There are even cubic units on it. How would I describe that in an equation? Yeah?
Y times x squared equals 36.
Right. The volume of a box is length times width times height. That's x squared y must be 36. This is my constraint equation. What is the objective here? Yeah.
To get the minimum surface area.
Minimum surface area. So surface area is what we want, is our objective. How would I describe that in an equation? Surface area. Roll this speed. How do you find surface area?
Is there a bottom on this box?
Yes, there's a bottom. There's no top.
Okay.
So it's an open top box. Yeah. So, yeah, right, top. Job.
You just like have
Out of there is all the faces, so what would we get?
x squared plus xy. Yeah. X
So x squared is for the right side.
Yeah.
The left side would also be x squared. So 2x squared. This is for the left and right. Then
2xy. Then parentheses xy. So you got the left.
here,
front
this
and
is, that's x times y. Front and back is x times y. Then there's the base though. What is the base?
back. xy.
It's also xy. So there are 3 xy's. And that is the base, front, and back. So that is my objective equation. So now I have 2 equations that describe this scenario. One describes my restriction, the other one describes what I want to maximize or minimize. Now, what we're going to do is, can't do with 2 variables, so I'm going to solve for one variable here, plug it in there. Who do you want to solve for? Yeah.
Why?
Why? Why would you solve for y?
Because then, if you solve it for volume, you can plug it in on the surface area, because it's there's only one y.
Yeah, but there's also only one x in, or is it just an x here? Why not solve for x?
Does it make the square root?
Does it make a square root? Again, it doesn't matter who you should solve for in general, you'll ultimately get the right answer. But in this case, I think it's easier to solve for y, because if I had solved for x, I have to use a square root. Okay, so solving for y is going to be the easier one, so I'm going to say, okay, from here, y is equal to 36 over x squared. And so that means I can write my area as just replacing the y with 36 over x squared. So this is 2x squared plus 3x times 36 over x squared. So that's my new objective function. Simplify this a little bit. 3 times 36 is what? 108. 108 over x. So that's my new objective function. At this point now, I actually want to minimize that function. One thing you notice, this is not a polynomial. You're dividing by x, and this is a kind of function that you don't really have a general or well-known formula to find its maximum or minimum. So we would use calculus. Again, the extreme cases are you can put 0 resources on one and put all the resources on the other, but that wouldn't create a box, so we're going to ignore the endpoints, and we're going to just look for the local maximums and minimums, which means we need to start talking about derivatives. Derivative of this is going to be 4x minus 108 over x squared, and I'm going to set this equal to 0 or undefined for critical points. Now clearly, if this is undefined, that would mean that my x is 0. If my x is 0, I don't have a box, so I'm going to ignore the undefined case. It's not relevant to me, and I'm simply going to solve for this equation equals 0. So we have 4x minus 108 over x squared equals 0. How do I solve that for x? Yeah.
With the 108 over x squared on the right side multiplied both by x squared, you get 4x squared equals
Right, so you get
108.
4x cubed equals 108.
Divide both sides by 4, and you get x cubed equals 27.
So your x cubed would be equal to 27, and therefore your x will be equal to 3. And again, you could go over here and test that and blah blah blah, you'll realize that that works. So now, this leads us to 6. We were asked to design the box, which means we need to talk about its dimensions. So I'm going to say when x equals 3, y is equal to, y was equal to 36 over x squared. It's 36 over 9. So this means dimensions, if I were to design this box, be 4 by 3 by 3 inches. This is a box with square ends. Its volume will be 36, and it will have the smallest possible area for that volume. Right? Again, there are tons of different lengths that you could imagine giving to this box, but that's the best one for this scenario. Any other arrangements of dimensions that gives us that volume of 36 will necessarily have a larger area than this one. Any questions? Let's go again.
Oh, my question.
Yes.
Does it ever happen that if you're trying to find the minimum or maximum, but you get the other line when testing the critical points? If you have like only one critical point?
In class, no. In practice, probably. So sometimes you're looking for something that you think exists, but maybe just doesn't exist. And so you might want to find a maximum thing, but maybe there is no theoretical maximum. Then you might run into issues like that. So you might have a minimum, but no maximum. But in general, if I'm going to ask you something in this class, it's going to exist. So you don't have to worry about that. So the worst case scenario you would have to worry about is the situation in which in step 4 you find several answers, and then you have to test which one you want. So you might have some minimums and some maximums, and you have to check what you want. But other than that's not going to really get any more complicated than that. Most of your work should happen in steps 2 and 3 to be able to come up with a diagram and then figure out the equations. But since 3 is also rectangular, let's jump to example 4. You guys can try the others on your own time. So here we want to create a cylinder that holds 8,000 pi cubic meters of liquid, and you want to find the dimensions that will minimize the amount of material needed to make it. You want to minimize surface area. This is a different kind of object. So step 1, we're going to read, which we just did. Step 2, I'm going to draw a picture of the situation I want. It's a cylindrical can. And it's of course open, so there's no top. Yeah, so it's a can without a top. And so there is a base. I can imagine that its radius is r and its height is h. So this is the guy that I want to talk about now. What's the constraint here? Volume is again the constraint. The volume must be 8,000 pi. You know volume is a constraint. One way because it says that's what it should hold, and you usually measure the space that something holds with volume, but also the units tell you its volume because it's cubic units. And what's the volume of this kind of object? Pi r squared h. Pi r squared h must be 8,000 pi. Then you're going to find the objective. And what's going to be the objective here? Again, it's surface area. How do you talk about the surface area of this object?
2 power h plus power squared.
2 pi r h plus pi r squared. You guys see where she got that from? How she got it? The idea is with a cylinder, you can slice it along the edge and then unfold it. Right? It'll unfold into a rectangle, and then the base is going to be just that disc. But this is the rectangle that you wrap around that disc, so the length of that rectangle must be the circumference of the circle, 2 pi r. And of course the height is going to be h. And so the area of the side is 2 pi r h, which is where this comes from. The disc, which is the base, is just a disc of radius r, and so that's going to be pi r squared per area. If there was a top, you would have 2 pi r squares, but there isn't. So that's my constraint and objective. This brings us to step 4. I'm going to solve for one variable in the constraint, plug it into the objective. And in this case, again, because I don't want to have to deal with radicals, I probably solve for h. So the pi's would cancel, and I would end up with, now my area is going to be pi squared plus 2 pi r times that h. R squared would cancel. This brings us to step 5. We're going to want to minimize a. Means I'm going to want to find its derivative. 2 pi r, and its derivative with respect to the radius, of course. So, minus 2 times 1,000 over r squared. Is set equal to 0 or undefined. Get our critical points. Undefined happens when the radius is 0. Obviously, if that's the case, I will not have a can. I'm going to ignore the undefined situation, and I'm going to go with the 0 situation. So now, if I set that equal to 0, I would have 2 pi r minus 2,000 pi over r squared equals 0. I can cancel 2 pi from both sides by dividing both sides by 2 pi. Similarly, I can multiply both sides by r squared, that would give me an r cubed. And r cubed equals 8,000. This means r is the cube root of 8,000, which is 20. So the radius of 20 is what I need for this situation. Again, I test that. At 20, you realize they're going down. So I plug in like 1 and 21 into the A prime. And again, here we're at for dimensions. So I'm just going to tell them the length and the height and the radius. So we know that the radius needs to be 20, and in that case the h is going to be 8,000 divided by 20 squared. That's 8,000 divided by 400, the zeros cancel, and we get 20 plus 10. So this means radius should be 20 meters, and the height should be 20 meters. So practice more problems. There are a bunch of examples left over that you can go through for extra practice. I pretty much ignore the inventory cost situation, so I won't test you on that. But things like these and more are fair game. We'll see you guys tomorrow. So your quiz tomorrow is, I guess the bonus would be stuff like this optimization, but it's on like curve sketching. I'm gonna give you a curve sketching.